Okay, so I had some questions about the last problem on Kepler's third law. Well, just as a quick summation of Kepler's three laws, the first law states that planets in orbit move in a elliptical manner, not a completely circular manner. Although most of the planets that we have don't orbit in that much of a elliptical pattern. The eccentricity that you should have played around with yesterday is close to zero. But the second law states that basically equal areas are swept out by equal amounts of time. And so when it's moving in elliptical orbit, what that means is when an object is closer to the sun, or the object that it's orbiting around, in our solar system it'd be the sun, it's moving slightly faster than it would if it's farther away, because it's got to sweep out the same amount of area. And then Kepler's third law is basically this right here, with the relationship between the orbital period squared and the orbital radius cubed. And so they had that relationship there. And this is called Kepler's third law. And so this is a very common equation that's associated with Kepler's third law, and that's what you should be using on that final problem here. And so I just took a different problem, not the same problem, but the different problem, and I'm going to solve it. So the key thing about solving a Kepler's law problem is you have to have something to compare the motion or the orbit to. And so this problem right here is clearly talking about Mars. And so I'm going to let Mars represent this 1 over here. So anything that's representing by 1, I'm going to represent that with Mars. And so I'm going to talk about the orbital period of Mars. So I'm going to ask myself, do I know what the orbital period of Mars is? Well, yeah, I do. It tells me up here that it's 1.88 years. And so it's 1.88 years. And then I'm going to want to square that guy because it's the orbital period squared. And so I'm just going to plug that straight into the equation like so. And I'm going to square that puppy. Just like that. Okay, so then I'm going to ask myself, do I know about Mars? Do I know the orbital radius? Well, no, I do not. And so therefore, I'm just going to hit enter here, then on space, it just is centered up. And I'm just going to call that, I don't want it in the superscript, I'm just going to call that r to the third. And so I do not know that. And so now the question is, do I have anything else that I can compare it to? For instance, do I have something else that I know for a fact about the orbital period and the orbital radius? Well, yes, I should. Something else that orbits around the sun is obviously us. We're on Earth because we're orbiting the sun as well. And so therefore, I want to compare it to Earth. And so Earth has an orbital radius, or as an orbital period of how much? Well, that should be an easy one because we live here. Orbital radius, how long does it take to go around the sun? Well, that's 1 year. And so I'm going to say 1 year, and then I'm going to close parentheses, and then I'm going to go squared, just like that. And then, underneath that, I'm now going to think about, okay, do I know the orbital radius? Well, I could look it up. I could do that. However, you're going to learn this today. An astronomical unit is a measure of distance. It's talking about the sun. Basically, an astronomical unit is the distance from the sun to the Earth. And they define it as 1 astronomical unit. And so the distance from the Earth to the sun is 1. Again, don't want to be in superscripts. It's 1. I'll put in parentheses. 1 AU, what we call an astronomical unit, and then I'd want to cube that guy. But the beautiful thing about this is the cubing doesn't really do anything because the cube, 1 cubed, is still 1. And so basically I have gotten this equation. So over here is Mars, over here is Earth, and I just want to compare the orbital radius and period of both of them. So the simple way to do that is to just calculate it. Now cross multiply and divide is a beauty. And so what I want to do is I want to take 1.88 and I want to square it. So 1.88 times 1.88 is a value of 3 3.53 years squared. And then I'm going to multiply that times 1 AU cubed, and so 1 AU cubed is just 1, and so therefore that's the units on that would just be AU to the third power. And then I'd set that equal to the cross multiple of the other side, which would be 1 year squared, which would just be year squared. And so I'm just going to write 1 year squared times r to the third. So then how do I solve for that? Well, then I divide by 1 year squared, and when I do that, the year squared is going to cancel, so therefore that's going to leave me with 3.53. Again, don't want to be in superscripts. It's going to leave me with 3.53 years. Oh, years canceled. So that's going to leave me with AU to the third power is equal to r to the third power, and now all I need to do is cube root that. Now, unfortunately, on my phone, I don't have a calculator on me that calculates that, but all you have to do is cube root that, and that should tell you the astronomical unit of the distance from the sun to to Mars. Hope that helps.